Imagine a flash of energy so intense that it blinds our instruments. In October 2022, a sudden burst of high-energy gamma rays swept through our solar system and temporarily blinded most space-based gamma ray detectors. Astronomers quickly dubbed this event the BOAT, short for brightest of all time. It was a gamma ray burst, one of the most powerful explosions in the known universe. In fact, gamma ray bursts, or GRBs, can unleash in mere seconds as much energy as our sun will produce in its entire 10 billion year lifetime. These cosmic eruptions are now understood as signals announcing the birth of black holes across the universe. So, what exactly is a gamma ray burst? A GRB is a sudden, intense flash of gamma radiation coming from space. They were discovered by accident in the late 1960s when satellites searching for nuclear explosions detected mysterious cosmic blasts instead. For decades, their origin was a puzzle. Today, we know that there are two major types of GRBs, defined mainly by their duration. Short GRBs, which last less than 2 seconds, and long GRBs, which last longer, sometimes multiple minutes. This simple difference in duration actually points to very different cosmic catastrophes. Long-duration GRBs are linked to the explosive deaths of massive stars. Picture a star many times the sun's mass that has exhausted all of its nuclear fuel. Its core suddenly collapses under gravity, creating an intensely dense object, often a new black hole, while the outer layers explode outward as a supernova. In that instance of collapse, 2 jets of particles blast out from the poles of the newborn black hole at nearly the speed of light. Short-duration GRBs come from a different violent event, the collision and merger of 2 ultra-dense objects, such as a pair of neutron stars. When these stellar remnants spiral together and merge, the crash produces a new black hole and unleashes jets of high-energy particles. These short bursts are often followed by a fading glow called a kilonova, powered by the creation of heavy elements like gold and platinum forged in the collision's aftermath. So, how do we detect these blink and you miss it events? Astronomers rely on spacecraft that constantly watch the skies for gamma rays. NASA's SWIFT satellite and Fermi Gamma Ray Space Telescope are 2, for example. SWIFT carries a sensitive gamma ray burst detector along with onboard X-ray and optical telescopes that can swivel within seconds to focus on a burst location. When SWIFT detects a GRB, dozens of telescopes on Earth rush to observe the location in X-ray, visible light, and radio waves. This aftermath can linger from hours to weeks, giving scientists a plethora of data long after the initial gamma ray flash has faded. Why do gamma ray bursts matter? For one, they let us probe into the past. GRBs are so luminous we can detect them across the universe. In many cases, by the time their light reaches Earth, the burst happened billions of years ago. That means each GRB we see is like a message from the past, giving scientists data on the conditions of the early universe. GRBs are also tools for fundamental physics. Their razor-sharp, high-energy flashes allow tests of whether the speed of light varies with energy or whether the constants of nature have changed over cosmic history. In the end, every gamma ray burst is a flashbulb, announcing the universe's most extreme moments. And from that brief light, we learn how stars die, how black holes are born, and how the cosmos itself evolves.